Hi guys, welcome to Night Science Stories. Settle in, breathe at an easy pace, and let your thoughts soften like a shoreline at twilight. Tonight we will listen to the quiet conversation between the moon and the ocean. Imagine the Earth wrapped in a thin, mobile shell of ocean water. It is not very deep compared with the size of the planet. If the Earth were a smooth sphere, the ocean would be a film of blue only a few kilometers thick. Because water can flow, it can respond to small differences in pull. The moon tugging on one side of Earth does not yank the whole planet. It draws very slightly more on the side that faces it and very slightly less on the far side. This tiny difference is enough to raise a broad swell in the ocean. Think of it as a long, slow hill of water that tries to stay lined up with the moon as the Earth turns. The height of that hill in the open sea is rarely more than a meter or two, often less than that, but its span is vast, stretching across entire ocean basins. A faint force applied to a compliant medium over a very large area becomes an unmistakable signal. The idea that two tide crests exist at once can feel counterintuitive until we look at the whole system. The moon pulls more strongly on the near side of Earth because it is closer and less strongly on the far side because it is farther away. Inside the Earth-Moon pair, there is a shared center of motion, the common balance point where both bodies orbit. Water on the near side is drawn a little toward the moon and away from the center of Earth. Water on the far side is left a little behind because the solid Earth is pulled a little more strongly than the distant ocean. The result is a pair of bulges, one facing the moon and one opposite the moon. Between them, along the band where the pull is balanced by the spin of the Earth, the sea surface is slightly lower. As the Earth rotates, coasts pass under these slow-moving hills and valleys of water, like a city standing beside a river that rises and falls as the river sways from bank to bank. The sun also speaks into this conversation. Though the sun is far away, it is immensely massive and it adds its own tide-raising pull. When the sun and the moon line up with Earth during the times of new moon and full moon, their tugs join. The two bulges grow taller and the lows grow lower. Along coasts, you can hear mariners speak of spring tides. Spring here means to leap, not the season. Water doesn't remember our calendar. These higher swings, born of alignment, are common and predictable. People who harvest shellfish plan their work around them. Birds that nest on low islands listen to them as to a clock. When the sun and the moon are at right angles as seen from Earth, the picture changes. During the first and the last quarter of the moon, the solar pull works sideways to the lunar pull and the sea does not stretch as far. The higher waters do not climb quite so high and the lower waters do not fall so low. These are called neap tides, quiet waters that leave a gentler mark along the shore. After the stronger spring tides, neap tides bring a slower breathing to estuaries and tidal creeks. Animals that depend on precise water levels, like some crabs and wading birds, adjust their foraging to this softer beat. Fishermen watch the neapy days for calmer currents in narrow passages. While the sun and the moon set the rhythm, the spin of Earth sets the tempo you feel at any single place. The Earth turns once in about 24 hours. The lunar bulge makes a full lap relative to the surface in a little more than that, because the moon moves forward in its own path around Earth. The interval between one high tide and the next high tide at the same dock is about 12 hours and 25 minutes. You can test this with a notebook near any harbour. Record a time when the water touches a mark on a piling. Return the next day at the same clock time and you will find the sea a little late. That small daily delay is the voice of the orbiting moon. Now add another element of motion, the effect of Earth rotating beneath moving water. In the northern hemisphere, currents are turned a little to the right of their direction of travel. In the southern hemisphere, they are turned a little to the left. This is the Coriolis effect, not a force from outside, but a pattern that emerges in a spinning frame. Because of it, the large-scale tide waves tend to rotate around ocean basins. Along the edges of continents, the tide signal can press into the coastline as a special kind of wave that keeps the coast on one side and deeper water on the other. These are Kelvin waves, quiet runners that carry the tide for great distances while hugging the land. In the northern hemisphere, they creep with the coast to their right. In the southern, they keep the coast to their left. Even in their quiet ways, they help explain why the same moon can lead to very different timing and heights at ports that are not so far apart. The most basic picture of tides is called the equilibrium view, where the ocean simply bulges under the moon and the sun, and the Earth turns under those bulges. It is a useful introduction, but real oceans have continents, peninsulas, islands, and irregular bottoms. The tide cannot sweep smoothly under a landmass. It must detour, reflect, and sometimes slosh inside a basin as water would in a broad bowl. This moves us to the dynamic view of tides. In this view, we track the tide as a wave that travels, bends, and even sets up standing patterns like the sway of tea in a cup after you nudge it. The geometry of basins and the depth of water matter as much as the pull that starts the whole show. When an ocean basin or a long gulf has a natural period of slosh that happens to match the timing of the incoming tide, the two motions add together. The result is resonance, which can produce spectacular heights. The great stage for this is a bay with a long, narrowing shape that focuses the wave. Many listeners have heard of a Canadian inlet where the sea climbs a cliff of coastline twice a day. The geography there, its length, its depth, and its mouth open to the ocean, all help the bay swing in step with the passing tide wave, piling water higher than almost anywhere else on Earth. In smaller bodies of water, such as long harbours or sounds, similar standing waves called seiches can grow when wind or air pressure pushes water and then lets it rebound. Seiches and resonant tides together give local coasts their personality, which you hear in the way a marina creaks or mudflats glisten. Approaching land, the tide wave meets the continental shelf, that wide underwater terrace that rings many continents. The shelf is shallower than the blue depths offshore, and the front edge of the tide wave slows down. The water behind continues to move faster, so the wave grows taller much as a line of runners compresses when the leaders slow. Friction with the bottom also changes the timing or phase of the tide, so the moment of high water may arrive later on a beach than offshore. In some places, a large river mouth and a narrowing channel act like a horn, raising the tide even more as it pushes inland. Where the shape is just right, a tidal bore can form, a single rolling front that travels up the river as a small wall of water. In other places with broad shelves and many sandbanks, the tide becomes a complex lacework of streams and whirlpools that turn vast sand shoals from one shape to another through the seasons. All of these ingredients come together to decide the local style of the tide chart. Some coasts experience 2 high waters and 2 low waters of similar height in each lunar day. This is called a semi-diurnal regime. Many North Atlantic shores follow this pattern, almost like a heartbeat that keeps even time. Other places see only 1 high water and 1 low water in about 24 hours. That is a diurnal regime found in parts of the Gulf of Mexico and along some Pacific islands. Still, other coasts show a mixed regime with 2 highs and 2 lows, but of different magnitudes, a rhythm that feels syncopated. The mixture reflects how the lunar and solar pulls arrive at a particular harbor after winding around islands and shelves and after being bent by the spin of the Earth. Local bathymetry, the undersea topography, is the arranger of this music. Let us stay a little longer with the opening concept because the theme of small cause and large effect carries useful calm. The moon is not trying to lift towers of water the way a person lifts a stone. Instead, it nudges parts of the ocean very slightly differently, and water does the rest by flowing. Because the ocean is connected, the response is not loud in one place and silent in another. It is a low rumble everywhere that rings more loudly where shape and depth allow it. Think of a child pushing a swing with gentle, regular taps. If the timing is right, the swing arcs higher with each pass. The taps are small. The motion grows large through patience and matching rhythm. So it is with the lunar pull and the geometry of seas. On a clear night, if you walk ashore as the tide turns, you can feel the meeting of cosmic order and earthly detail. The moon, alone in a cold sky, tells you one part of the story. The cove in front of you, with its curved beach, its rocks, and its channel, tells you the rest. The height and timing you witness are the sum of many small contributions that your senses fold into a single experience. The wind, if it has blown on shore all day, may have pushed the water up a little higher than the tables predicted. A passing region of low air pressure might lift the sea surface by the height of a few millimeters for every hectopascal drop, a small nudge that can matter during a very high spring tide. A distant storm can send long waves that ride in like extra breaths between the regular rise and fall. The simplicity of lunar pull meets the complexity of an earthly coast, and together they draw the line where your footprints will be erased. To weave together these ideas, picture a point in the open ocean, far from coastlines. There the tide looks most like the gentle hill of the equilibrium view, a broad rise and fall that does not vary dramatically from day to day. As the wave approaches land, the Coriolis turning begins to matter. Shelves bend the flow, and the wave is squeezed and reflected. Around the edges of basins, the tide rotates about quiet nodes called amphidromic points, where the height hardly changes, but the phase spins like the hand of a clock, pointing to a different hour at each surrounding port. Draw that map in your mind. Small circles drawn over offshore nodes, arrows swirling around them with numbers at coasts marking the time of high water as the wave sweeps by. It is a living atlas that never lies still. That moving atlas explains some of the striking records along the planet. In narrow passages where the tide must squeeze through a gap, currents can run like a river. Sailors time their crossings through these gates with care. In funnel-shaped bays that invite resonance, the sea climbs the shore in twice-daily strides that set world marks. In wide coral lagoons, the tide may be so damped by friction that the range is only a modest rise at the beach. And on isolated seamounts, as the tide flows around, it can create internal waves in the layered ocean that break like underwater surf, stirring nutrients from the dark into the sunlit layers above. Even where few people watch, the tide is at work as quiet labor. All living things along the shore have listened to this music for a very long time. Along rocky coasts, you can trace tidy bands of life that match the typical reach of the water. Barnacles and mussels occupy a high zone where they are wetted twice each day but spend long hours in air. Seaweeds drape lower ledges that are rarely exposed. Eelgrass makes gardens in the soft mud of estuaries where still water follows just behind the turning points of the tide. Crabs leave their burrows when the flats are warm and shallow. Wading birds time their flights to arrive when the mud is uncovered and rich. Human communities do the same. Fishers know the slack moments when a tide turns and nets can be set without strain. Bathers learn to meet the ocean when the surf is kindest. Coastal people have turned the heartbeat of water into calendars and stories. When you recall that the period between one high water and the next at the same place is about 12 hours and 25 minutes, you can see why the timing marches slowly through the day. A noon high water today becomes a high water a little after midnight in a few days. In some towns, you can watch street markets and ferry schedules adapt to that moving appointment. The tide chart is like a poem posted each day at the harbour. It anticipates not only the timing, but the height, whether the day will bring a gentle rise or a proud reach. People who work close to the water learn to read the chart with an intimacy that resembles the way a farmer reads the sky. Questions often arise when one hears that there are two bulges. If that is so, why do some places have a single high water most days rather than two? The answer is that the ocean is not a single clear belt. The path of the lunar tide wave is distorted by the shape of the basins and the presence of land. When an island shelf carves the wave, or when reflection mixes different frequencies of motion, the pattern that reaches a port may be dominated by a once daily component. Elsewhere, the twice-daily component is strongest. In many places, the two are of similar strength, and the result is a mixed tide with alternating high waters of different height. The melody is the same, but the harmony varies with every harbour. The forces that begin the tide also very slowly change the earth itself. As water is dragged across the seabed twice a day, energy is dissipated as heat, and a tiny amount of the rotational momentum of Earth is transferred to the Moon. Over great spans of time, the length of day has crept longer by tiny fractions of a second, and the Moon has drifted farther from Earth by small amounts each year. In the far future, this will change the pace and the power of tides. That thought is not meant to trouble sleep. It is a reminder that nothing in nature is permanently still, not even the slow dance between the earth and its companion. For now, you can take comfort in the steadiness of the cycle. In a remote cove, the sea creeps up through the grass, pauses and retreats, and the same motion is mirrored on a different shore across the world. The tide is one of the few truly global rhythms that the senses can perceive directly without instruments. You can extend your hand and feel it. You can sit at evening and watch a rock that was wet become dry again. You can row a boat and sense the moment when the current slackens and then begins to move the other way. All of this comes from a very slight difference in gravity across the diameter of a planet and from the patient turn of the Earth beneath a travelling wave. Let that thought be the constant line that weaves through the details. The moon calls with a force that is small. The ocean answers with a movement that is grand. The sun adds its accent, sometimes amplifying, sometimes softening. The spin of the earth guides the tide along coasts and through straits. Basins and shelves shape and sometimes dramatize the response. Out of these elements, you can build a mental picture of the tide that is both simple and rich. When you next see a diagram of phases of the moon, you may also see the quiet breath of bays and estuaries drawn around our planet. As the night deepens, imagine yourself aboard a gentle research vessel far offshore. The sea is not rough, only long swells under a sky of stars. A soft red light glows above the chart table. On the paper are arcs and lines showing the predicted times of high water at distant ports, and a penciled note that the tide here in the open ocean will be only a modest rise. The radio murmurs a weather forecast. A scientist steps out to release a float that will measure the tide as a small change of pressure with depth. The instrument will report the passing of the long wave, the very hill of water that began with the lunar pull many time zones away. You can feel the ship rise slightly and fall. You can feel the planet breathe. In the morning, that same wave will be running into a wide estuary. It will lift the river and reverse its surface flow for a while, bringing salt farther inland. It will slacken around docks so that boats can slide into their berths with gentler hands. It will creep over a flat and then slip away, leaving the shining paths of snails and crabs printed in the mud. It will rock the kelp forests and swing their blades in arcs that feed them fresh water. It will exploit every channel and curl around every island, always following the shape of Earth and the laws of fluid motion. And somewhere a child will build a wall of sand and watch it dissolve, not by chance, but on schedule, because the moon is passing a particular line in the sky. Allow all of this to form a single quiet image, a silver moon, a blue planet, and between them an ocean that is sensitive to the slightest difference. The story begins with gravity and ends at the tips of grass in a salt marsh. It is a chain without a broken link. As you drift toward rest, you can hold one thought with you. The world has many clocks. The tide is one of the oldest and one of the kindest. It keeps time softly, and it does not ask for our permission to continue. The music of the tides becomes clearer when we learn its alphabet. Oceanographers speak of harmonics and constituents, quiet notes that add together to make the daily song heard at a harbour. Each note has a name and a period that never changes. The most powerful of all is the lunar semidiurnal constituent called M2. The letter tells you it is lunar. The word 2 tells you it repeats about twice in one lunar day. Close behind is S2, the solar partner that also repeats twice in one lunar day, but is set by the sun rather than the moon. Then come the slower once daily notes. K1 blends both lunar and solar effects into a single steady stroke and can dominate at some islands. O1 is mainly lunar and once daily. There are many others, such as N2, which is a smaller lunar partner to M2, and P1, which is solar and once daily. Imagine these notes as pure tones. At any pier, the water level you see is a chord, the sum of many tones at once. Scientists can measure a year or more of water levels, separate the record into these notes with patient mathematics, and then forecast the tide by adding the notes back together. It is as if we have learned the sheet music of that particular harbour. Once you hear the alphabet, you will notice the slow hands that modulate it. The moon does not simply circle in a perfect loop. There are several lunar cycles that touch the height of tides. The synodic cycle is the one we know from the moon's phases, the steady march from new to full and back again over a little more than 4 weeks. This cycle organizes the spring tides when sun and moon align and the neap tides when they stand at right angles. Another cycle is the anomalistic one, which tracks how the moon moves closer to Earth for a time and then farther for a time. When the moon is nearer, the tide-raising pull is stronger. When it is farther, the pull is gentler. A third cycle has to do with declination, the tilt of the moon's path north and south of the equator. When the moon rides high above one hemisphere and low above the other for many days, the once daily constituents become more prominent, and the two daily highs can differ. These 3 rhythms lay a slow pulse under the daily pattern, like a tide within the tide. Every so often these cycles line up and the sea steps closer to the land than usual, when the moon is near its closest approach and when it is new or full so that sun and moon align. The two conditions join. Ocean folk call the resulting higher waters Peregrine spring tides. Along some coasts, people have taken to calling them royal tides, a name that lives easily on the tongue. These are not floods born of storms. They are simply the regular spring swing made a little broader by the nearer moon. They can overtop sea walls that are usually just high enough. They can wake sleeping salt marshes and refill shallow lagoons. With thoughtful planning, they become useful. Communities that restore wetlands time their work to these visits from the larger tide. Photographers love the way harbours look when boats hover higher than usual beside stone quays. For those who live near low ground, these days bring a gentle reminder that the line between sea and street is not fixed by concrete but by gravity and the turn of the heavens. There is an even slower sway written into the tide through the tilt of the lunar orbit. The path of the moon is not anchored to one permanent angle. It nods slowly and predictably over a cycle that lasts about 18 years and a little more than a half year. This is the nodal cycle, when the node that marks the intersection of lunar and solar paths shifts. The range of lunar declination that the moon can reach also shifts. The result for coasts is a slow change in the relative strength of the twice daily and once daily constituents. In some harbours, the difference between the higher high water and the lower high water grows and then shrinks over this long cycle. Tide tables quietly include a correction for nodal stage, so that predictions stay faithful to the true rhythm. Marinas that were built during one part of the cycle sometimes discover that their clearances feel different nearly 2 decades later, even though the moon has not changed its mass or distance in any dramatic way. This very slow metronome is a reminder that the sea listens to distant geometry as much as to local wind. When we move from time to space, another form of tide map appears, one that looks at first like a dance chart. In the open ocean and in wide seas, the tide often rotates around points where the range is tiny. These are amphidromic points, places of near silence. Around them, the hour of high water changes as steadily as the numbers on a clock face. Follow a circle around such a point and high water marches forward hour by hour until you're back where you began. The cause is the combination of basin shape, the depth of water, and the turning of earth that bends the tide into a rotating wave. On a map of the world, there are many such systems, some large and some small. Coasts on one side of an amphidromic system will see the tide wave arrive from the south, while coasts on the other side see it arrive from the north. Draw lines on such a map and you will see bands where the tide reaches greatest height and other bands where times change quickly but heights remain modest. Navigators may never use the word amphidromic at sea, but they learn the pattern by touch from the way currents set in a strait and from the order in which harbours begin to stir. Beneath the familiar surface slosh, there are fronts and waves that most eyes never see. Where water masses of different temperature or salinity meet, a narrow boundary can form, a tidal front. Along such a line, the tide acts like a hand at the edge of a rug, rocking the boundary back and forth. The energy that is lost at the edge becomes turbulence, which mixes nutrients upward from dark layers into the lighted zone where phytoplankton can use them. At some banks and shelves, this mixing makes seasonal blooms that feed fish and birds and the people who depend on them. Still deeper within the layered interior of the ocean, the tide can excite internal waves that are 100 meter tall yet calmly invisible at the surface. They move slowly, break on underwater slopes, and stir the abyss the way a spoon stirs a pot. Such mixing helps set the temperature structure of the global ocean. The moon, working through tides, therefore plays a quiet role in the climate machine by helping heat and salt to reorganize in the depths. Return now to the shoreline and walk the living stair that the tide draws twice each day. This is the literal world, the band between low tide and high tide where rock and sand and mud spend part of each day in air and part underwater. Life here has learned the art of patience and the art of clinging. On wave-washed headlands, barnacles build close packed cities whose walls resist drying winds. Mussels braid themselves with byssal threads so they become one strong mat that waves cannot strip away. Seaweeds anchor with holdfasts shaped like fingers gripping a crack. In sandy places, clams and worms move with the tide, riding the wet front line a little up and then a little down. Every step has its own guild of residents. High on the rocks, splash zones host lichens and tough snails that graze on film. Lower down, tide pools become pockets where fish and anemones endure hours of isolation until the sea returns. If you have ever wondered how a shore can feel both busy and calm, think of the clock that runs there. It is shorter than a day, yet it never tires. That steadiness allows creatures to evolve exquisite timing. Timing shapes bodies and behaviors from the inside as well. Many coastal animals do not simply react to the arrival of the tide. They predict it with internal clocks that keep circadial time. A shore crab held in still water far from the beach will still become more active at the hours when it would normally forage on exposed flats. Mussels open and close in a schedule that matches the waterline at their home rocks, even when kept in a laboratory at constant water level. Some birds that feed on intertidal worms adjust their flights and their stomach emptying to match the hour when food will be available. These clocks are not identical to the daily circadian ones that match daylight and darkness. They are built of cellular chemistry that can be entrained by gentle floods and ebbs and then run free for many days like the echo of a bell. The moon has been ringing this bell long enough for genes to have learned the rhythm. In this way, the story of gravity writes itself into the molecules of crabs and clams. The patient push and pull of water moves sand and mud in ways that no single wave ever could. Along shallow coasts, the tide sets up currents that accelerate in narrow places and slacken on wide flats. Each pulse can pick up grains for a moment and let them settle in a different place when the speed falls. Over weeks and months, sand is sculpted into ridges and ripples whose crests mirror the path of strongest flow. Where two tidal streams divide a channel, a sandbar can grow like the tongue of a river delta. On broad shoals that feel a steady two-way sweep, long tidal dunes march very slowly across the bottom, developed by the alternating stress of flood and ebb. Where the tidal ellipse is a tight circle, mud can be winnowed from sand to form clean banks that show delicate current marks when the water leaves them. Harbour masters learn these rearrangements as if they were the moods of a neighbour. Channels must be dredged where bars move. Beacons must be shifted to guide boats over shifting ground. What looks from a cliff like a simple beach is in truth a mosaic laid by countless individual grains travelling one short jump at a time. The meeting of river and sea is the stage where all these strands join. An estuary is not merely a drowned valley, it is a breathing device. With each flood, the tide pushes salt water inland along the bottom, while the river slides seaward above, cleaner and lighter. The result is a salt wedge that advances and retreats. Where the two layers shear against one another, small eddies mix fresh and salt into a third flavour that is brackish. The mixing is strongest where bottom roughness and channel turns stir the flow. To see this structure with your mind, hold a clear glass of water. Pour in a thread of blue dye at the bottom and a thread of clear water at the top, and then slowly tip the glass from side to side. You will see layers and interleavings that resemble the estuarine dance. Life thrives where the mixing is real but not too violent. Oyster reefs flourish on firm ground within reach of the salt wedge, filtering water that brings them food from both river and sea. Marsh grasses grow in fans along the banks where fine sediment is trapped by their roots, building ground that keeps pace with the daily rise and fall. People have long built their towns at these meetings, for they offer calm water and access to inland farms and to the open coast. The alphabet of tide notes, the lunar cycles that weight those notes, the large-scale dance around quiet ocean centers, the hidden fronts and internal waves that stir the deep, the literal belts of rock and sand where life has made a truce with exposure, the internal clocks that keep time with moving water, the labor of tides that carries sediment grain by grain, and the estuaries that translate between fresh and salt together. give the tide its full meaning. It is not only a rise and fall, but a composer of landscapes and a tutor of living things. It writes deltas and bays. It times migrations. It shapes human plans whether we notice or not. Consider a night when the moon is bright enough to cast a silver path over a bay. Somewhere offshore, M2 is running at full strength, its companion S2 adding or subtracting a little depending on the angle of the sun. The once daily K1 and O1 notes provide a slow undulation that will make one high stand a little higher than the next. If the moon happens to be near its closer point in the long anomalistic swing, the tone will be fuller. If the nodal cycle happens to be in a phase that emphasizes once daily motion, the two high stands will differ perceptibly. The rotating tide around the nearest amphidromic point will decide whether it arrives from the south or from the north. Over the shelf, a quiet Kelvin wave will lean against the coast and help guide the pulse through the bends of the estuary. At the boundary between a cool ocean tongue and a warmer shelf, a tidal front will tremble, mixing trapped nutrients upward. Down in the interior, an internal wave will be climbing the slope of a bank and breaking like a slow avalanche. On the rocks, a row of mussels will tighten slightly as a ripple of pressure tells them that a new hour is coming. In the marsh, a small crab will test the air with its antennae and come out on schedule. On a sandbar, a new rib of grains will be laid, and an older rib will soften. And up the river, a salt wedge will pause, then begin to reverse its direction, while a heron steps with perfect timing onto the fresh, exposed flats. Reading the tide becomes, in this way, an act of calm literacy. The names M2 and K1 are not merely symbols in a table. They are letters that spell the behavior of water where you stand. The cycles of the moon are not only astronomical, they are practical announcements to shellfish harvesters, surfers, and engineers who plan bridges. The amphidromic map is not only an academic drawing, it is a chart that tells a sailor which way the current will turn under a certain headland. Tidal fronts and internal waves are not only studies in a journal, they are engines that feed fisheries. The littoral is not just a strip of inconvenient wetness for builders. It is a layered city whose residents keep the shore resilient. Biological clocks are not curiosities. They are the way shore life makes a living. Sediment transport is not dull. It is the hand that moves the pieces of a mobile sculpture. Estuaries are not merely places for port facilities. They are complicated hearts that circulate fresh and salt. If you ever wish to learn this literacy for yourself, pick one simple place. A short jetty will do, or a tidal creek with a footbridge. Visit it through one lunar month. Bring a small notebook. On each visit, write the phase of the moon. Whether new or slender crescent or bright round disk, write the time you arrived, not by digits, but with the words morning or afternoon or near dusk. Look at a piling or a waterline stain and write whether the tide is higher or lower than your last visit. Watch for the direction of the tiny floating leaves. Listen for the sound the current makes against the stones. Mark in your mind when the fiddler crabs come out or when sandpipers begin to run. After many visits, you will begin to hear the separate notes. You will know without looking at a table that the two high waters of a mixed regime are falling out of symmetry because the moon has climbed high in declination. You will sense that a higher than usual spring tide is coming because the moon looks a touch larger and brighter than the week before. You will become intimate with the idea that the sea is not a single body, but a mosaic of moving water. Under this soft education, you may find yourself experiencing a form of comfort that used to belong to farmers who knew the habits of their fields. The tide gives the same gift, only in water. Understanding does not make the sea less mysterious. It makes the mystery friendlier. The large cycles from the synodic to the nodal become like seasons layered inside seasons. The daily swing becomes the metronome that holds them together. From this quiet vantage, the moon is not only a distant sphere, it is the conductor of real events that touch marsh grass, sand grain, mussel shell, and human plan. Salt marshes and mangrove forests teach a gentle lesson about how tides build shelter. Where the land is soft and low, the regular rise and fall of water lays down fine grains of silt and clay. Marsh grasses grip those grains with a patient weave of roots, raising the ground a little each year, often by only a few millimeters, yet always in step with the water that nourishes them. Every flood brings suspended particles and dissolved nutrients. Every ebb leaves a thin film of new soil. In temperate regions, cordgrass stands like a green comb, slowing the flow and catching more of the soft rain of mud. In the tropics, mangrove trees take over the same apprenticeship with the tide. Their arching prop roots and pencil-thin breathing roots create a maze where water lingers long enough to drop its load. Young fish hide among the pillars, crabs graze on the leaf litter. Birds come with the turning of the light to hunt. These tidal forests also store what scientists call blue carbon. Leaves become peat. Roots turn into a quiet, fibrous library that can lock away carbon for centuries if left unbroken. When storms arrive, the pliant stems and roots turn violent water into slow water. A surge that would gnaw at a bare shoreline spends itself in the soft resistance of stems and trunks. Villages behind intact mangroves and marshes often see flood levels lower and currents gentler. The tide that builds these living edges is the same tide that protects them, a rhythm that both gives and guards. Coral reefs and their wide flats live by another chapter of the lunar book. On clear tropical evenings near the turn from spring tide to neap or back again, entire reefs take their cue from the moon. Corals release packets of eggs and sperm in mass events that last a few warm nights each year. The timing is so certain that scientists can plan their work weeks in advance by reading the phase of the moon, the water temperature, and the gentle slope of the tidal curve. Flood tides carry the fragile bundles away from the hungry mouths that live on the reef. Ebb tides leave parts of the flat exposed just long enough for air and sunlight to clean the surface, a natural reset that keeps some rivals in check. Fish that use the reef as a nursery match their movements to the tide as well. Juveniles ride the incoming flow to seagrass beds and mangroves where they can grow in safety, then return with the outgoing flow as they mature. On the long, thin platform of a reef flat, a difference of only a few tens of centimeters in water level can change the entire script. The tide writes calendars for mass spawning. It schedules the cleaning of tide pools. It opens and closes the door between lagoon and open sea in a way that makes the reef both sheltered and refreshed. Near the poles, the tide whispers through ice. The floating shelves that extend from Antarctica and from Greenland bend gently with every rise and fall. The creaking sound that explorers hear at night is the flex of a slab as large as a country. Beneath these shelves, tidal currents move through subglacial channels like rivers under a roof. They bring slightly warmer water into caves of blue light and carry colder, fresher water out, balancing the melt and the freeze. Satellites can see the tide in the ice as faint ripples of motion that repeat every 12 or 24 hours. Seals find breathing holes where fracture lines open and close to the rhythm of that lift. Penguins and polar bears time their crossings to the stable hours when the water sits still. In the darkness under the ice, small crustaceans gather where tidal mixing brings the finest particles. Even in a world that looks frozen and still, the moon sets a slow metronome that keeps the entire sheet breathing. Where the geometry of water and land line up just so, the tide becomes a theatre performance. The Bay of Fundy, between the Canadian provinces of New Brunswick and Nova Scotia, holds the world's best-known stage for extreme range. The basin length is tuned so that the natural slosh matches the twice-daily beat of the lunar tide. The result is a range that can exceed more than 15 meters between low and high on certain days, enough to empty coves entirely and to leave boats resting on the ground like stranded beetles until the water returns. Farther north in Ungava Bay, the funneling effect is even greater in some inlets, and the bore and range can be astonishing for places so far toward the Arctic. Across the ocean, the shallow plains around Mont Saint-Michel in France turn from land to mirror and back again as the tide rushes across the flats. The abbey stands like a stone mast above an ocean that comes and goes. In these places, people build staircases down cliffs, not with steps, but with anchor rings for moorings at different states of water. The local vocabulary grows rich with words for the many ways that water can arrive and depart. Sometimes the tide comes not with a gentle slope, but as a moving wall. Tidal bores occur where a strong flood tide runs up a river whose mouth is shaped like a funnel and whose bed is shallow enough to focus the incoming water into a single push. The Qiantang River in China hosts a bore that has been famous for centuries. It runs as a rolling cliff of water that can carry small boats with it if they are not carefully prepared. The roar can be heard far upstream before the crest arrives. In the Amazon, the pororoca is the name given to a bore that rises on certain days and travels against the flow for many kilometers. Surfers have learned to ride it, gliding past forest and floating villages on a wave that lasts longer than any ocean swell. On the River Severn in Britain, the bore sweeps around bends that reveal it in a long, shining line. Bores reshape channels, flatten sandbars, and require a special art of timing from pilots and fishers who use the rivers they visit. They are the dramatic cousins of the familiar tide, born from the same moon but given a different costume by the shape of the land. Every harbour has its rules and its windows, the quiet moments when a captain may enter or leave safely. An incoming ship seeks enough clearance under the keel, and so pilots wait for the higher water of a flood. But the safest moment is often at slack, when the current pauses between flood and ebb. In narrow channels, a strong cross-set can push a large hull toward a bank despite a powerful engine. tidal streams can also create standing waves and boils near bridge piers, patches of water that look smooth yet pull at a rudder with surprising force. Charts and tide tables are tools, but the best pilots also carry a mental map of the sequence of eddies that appear as the tide turns. Some ports with shallow bars put their harbour entrance along a natural deep that only aligns for a short span of minutes during certain phases of the tide. That span is the pilot window. A captain missing it must wait another 12 hours or more. Lighthouses, range lights, and modern beacons exist to shorten the margin for error. Yet, the rhythm of the moon still sets the master clock of arrival and departure. Long before computers, people set out to tame the tide with arithmetic and brass. Pierre-Simon Laplace cast the physics into equations that relate the motion of the ocean to the pull of celestial bodies and the turning of Earth. Later, in the 19th century, scientists learned to take long records from tide gauges and separate them into harmonic constituents with careful calculation. The result could be reassembled to predict future tides. Lord Kelvin designed an analog machine that performed this task with pulleys and chains. Each constituent was represented by a wheel and a shaft. As the shafts turned, their motions were added through a clever linkage to draw a continuous curve on paper. A trained operator could set the date and read out the heights and times for the year to come. These machines served working ports for decades. Modern methods use digital versions of the same idea. They now blend harmonics with models of basin shape and satellite observations. Yet at heart the promise remains the same as in the age of brass. If you have enough past notes from the Symphony of the Sea, you can compose the next movement with confidence. From orbit, satellites have added a new ear to the listening. Radar altimeters aboard missions such as Topex Poseidon and the series that followed measure the sea surface height by sending pulses of energy and timing their return. By flying very regular ground tracks for many years, these instruments can see the repeating patterns of M2, S2, K1, and the others stamped onto the global ocean. The maps that result show amphidromic systems as elegant spirals with colors standing in for phase and amplitude. Blind spots near coasts and ice still exist, but the broad picture is now sharp. Scientists combine satellite data with floating buoys and with models that account for seafloor depth, coast shape, and the gentle bend imposed by the rotation of the planet. The accuracy can reach a few centimeters when all methods are united, certainly close enough to improve tables for shipping and to test how tidal energy flows into the deep. This view from above has also shown that tides interact with seafloor mountains far offshore to generate internal waves that travel for hundreds of kilometers. The moon leaves a trace in places that no human eye can reach, and satellites learn to read it. Weather and tide sometimes walk hand in hand, and sometimes they do not. A storm surge is the pile of water driven toward a coast by wind and by the lower air pressure at the heart of a storm. It is not the same as a tide. But if the surge arrives at the same hour as a high spring tide, the two can add together. The barometric effect alone can raise sea level by about 1 centimeter for every 1 hectopascal drop in pressure. Strong onshore winds push water against the coast, tilt the surface, and slow the natural ebb. On quiet days, the tide drains estuaries in a neat pattern. Under a gale, the same estuary may hardly empty at all. Emergency planners learn to watch the calendar of the moon as well as the track of a cyclone. If a royal tide is due on the same weekend as an approaching storm, they order barriers closed and pumps prepared. Conversely, a storm that arrives on a neap tide may pass with minor flooding where the same storm would have been serious 2 weeks earlier. The dance is one of addition and subtraction, and the moon is often the partner that decides how dramatic the final movement becomes. Because the word tide is familiar and comforting, people sometimes use it for waves that are not tides at all. A tsunami is a long gravity wave set in motion by a sudden disturbance such as an undersea earthquake, a landslide, or a volcanic collapse. It can cross an ocean at the speed of a jet. In deep water, its crest is gentle and low, hardly noticed by ships. But as it reaches the shallows near a coast, the wave slows and rises, compressing into something high and fast. Unlike the regular turn of high and low water, a tsunami arrives as a train of waves over minutes and hours and then slowly eases away. It does not repeat every 12 or 24 hours. It ignores the phase of the moon. Warning centers read seismographs and ocean bottom pressure sensors to decide whether such a wave has been born. Sirens and alerts follow. Knowing the difference matters. A harbor that can handle a spring tide with ease may be at risk from a tsunami of only modest height because the speed and momentum are so great. The moon rules the daily life of the sea, but the rare great shocks come from the deep earth or the abrupt slip of slopes. The ocean holds both kinds of stories, the steady and the sudden, and learning the difference helps keep coasts safe. The farther you follow these chapters, the more the whole begins to resemble a single organism. Carbon rests in muddy roots that the tide feeds. Coral reefs attune their reproduction to the lunar cycle. Ice shelves flex and breathe on a schedule set by the moon. Extreme ranges and bores show what geometry can do. Navigation remains a craft of reading the right moment in a tidal day. Prediction grew from notebook to brass machine to satellite constellation without losing its reliance on listening to the true notes. Weather adds its own loud percussion, and sometimes it asks the moon for accompaniment. And out beyond familiar shores, the rare tsunami reminds us that gravity has many ways to travel. Through all of it, the same quiet force acts far above the sea, yet woven into every shorebird flight, every marsh blade, every pile of oyster shell that marks a human harbor. Energy from the tide begins with the simplest observation. Twice each lunar day there is moving water in places where at other hours the sea seems almost asleep. The oldest designs for drawing power from this motion look like mill ponds. A low wall across a narrow estuary closes when the ebb runs out, trapping water behind gates. When the flood returns, the gates open and water rushes through chambers where turbines spin. Later generations revised the plan by building open lagoons in shallow bays that fill and empty through turbine houses. Farther from land, in fast channels between headlands or islands, engineers lower nacelles into the current so that turning blades harvest energy from the steady flow, much as a wind turbine does in air. In some regions, long channels guide the stream to speed it just enough for practical work, yet keep the seabed open for fish and for drifting spores. What sounds straightforward becomes a conversation with the coast itself. A wall across a tidal flat changes how sediment moves. Mud that would have settled on the marsh gets trapped in a basin. If designers do not provide a new path for fine grains, the marsh behind the wall may starve and sink. Fish learn passage routes by smell and by current. A barrage that redirects the flood without careful passages can confuse migrations. Some species can use slow water and spiral fish locks. Others need large gates opened at precise times to align their inner compass with the taste of the river. Engineers, therefore, test their plans in scale basins and in computer worlds, where the water and the animals follow rules drawn from field notes. The best projects today borrow ideas from living shorelines. They use rock reefs and eelgrass to calm waves and to keep sand in place around foundations. Turbines are tuned to turn slowly so that a large fish sees and avoids the blades. Acoustic surveys check whether new machines add distracting noise to the underwater soundscape. Maintenance crews plan with birds in mind. If bolts must be tightened on a winter day when a tidal sandbar hosts thousands of resting migrants, the work moves to a quieter hour. When these questions are respected, a tidal plant can provide reliable power through decades, rising and falling with the moon exactly when a city needs the steady pulse of a base supply and a predictable complement to the gusts of wind and the glare of sun. When the questions are ignored, the same plant becomes an object lesson that a fast fix on the shore is never truly fast and never a fix. The moon is not the only place where tides write themselves into the story of energy. Far away in the cold spaces around giant planets, small worlds glow with a heat that they have no right to own. The reason is the same push and pull that moves our ocean. The little moon, called Io, orbits the huge planet Jupiter on an oval path. As Io swings close to Jupiter, gravity stretches it. As Io swings away, it relaxes. That millions of years-long massage needs the interior, melting rock and driving volcanoes that throw fountains high above the surface. Another moon named Europa carries a shell of ice above an ocean that is believed to be global. Tidal flexing within the ice makes it crack and moan. Below, the ocean may be kept liquid by the same slow kneading, with heat venting through the seafloor in a darkness lit only by chemistry. Farther out in the Saturn system, a small body called Enceladus shakes under a patterned pull from its parent planet and from neighboring moons. Through cracks near its south pole, the little world exhales plumes of water and salts that show it holds an inner sea in contact with warm rock. The mathematics that explains these places comes from the same set of ideas that explains our coastal tides. Gravity moves water and it also moves stone. When the pull changes rhythm, the motion turns to heat, and heat turns to geology and maybe to biology. In that sense, the tide is a thread that connects the bays where shorebirds feed with the hidden seas of worlds that we have touched only with our eyes. On our own planet, the tide leaves a very slow mark on time itself. Friction between moving water and the solid earth saps a tiny part of the energy of rotation. The moon that raises the bulges drags ahead of Earth by a small angle. Over deep intervals of time, this drag transfers angular momentum outward. The moon takes the gift and slips a little farther away from us by about 3.5 centimeters each year, a distance that is measured by bouncing light off small mirrors placed on the lunar surface by astronauts. Earth pays for the gift by turning a little more slowly. The length of one day grows by only a few thousandths of a second in a century. Far less than human senses can know, but enough that historians must account for it when they compare ancient eclipses recorded on clay tablets with the positions predicted by strict celestial mechanics. If one lets the imagination walk across millions of years, one sees the dance continue. Days will become longer. The moon will become a smaller disk in our sky. The tide will keep its rhythm, but the drum will beat more softly. That same thought leads to the next. What might the future of the moon and the sea look like long after us? As the lunar companion drifts outward, the strength of its pull on our water will wane. The sun, always the junior partner in our present tide, will carry a relatively larger share of the job. The mixed pattern of ocean movement will adjust, and the extremes of range in places that today host dramatic coasts may soften. The change will be so slow that continents will shift their outlines and mountain chains will rise and fall while the tide continues to visit twice each lunar day, as faithful as an old friend whose voice becomes gentler with age. The far future is a landscape of patience. Over calendars that make our eras look like a minute, gravity composes long notes that only geology can hear. Back in the living present, cities learn to keep time with the moon. Harbors have always done so. Now, entire metropolitan regions rediscover the clock. Transit stations post real-time warnings for underpasses that fill during extreme surges. Floodable parks settle along the waterfront as new kinds of rooms that welcome high water and release it without harm. Steps become broad stone shelves that vanish in high spring tides and display mosaics at knee-ape. Sports fields are built with soils and grasses that tolerate an occasional wet visit. Instead of carving channels that promise dryness forever, planners in the most forward-looking places choose amphitheaters with drains sized for once rare but now more frequent combinations of storm wind and royal tide. When a neighborhood sits in a low bowl, architects design homes that can float a little on concealed guides during the few hours of a deep flood and then return to their moorings. The view of the river becomes a shared full-length porch rather than a back fence. This is not surrender. It is a practical truce. By living with the known schedule of the tide and with the new statistics of storms, a city gains resilience and keeps its daily beauty. To work with water, one needs maps, and modern map makers trace lines that shift with each season. From orbit, satellite radars sweep the texture of the sea surface and can tell when waves run against hidden ridges. Along coasts, aircraft and drones carry instruments that use light pulses to measure terrain at centimeter scale, a method known in full words as light detection and ranging. When the tide is low, they scan mudflats and marsh blades. When the tide is high, they sketch the outlines of channels and banks. Together with gauges on pilings and with inexpensive sensors in citizen hands, these tools feed dynamic charts. On a phone, a mariner or a walker can see not only the present line of water, but also the line at the next hour and the line that will be there when a storm of a given track arrives. Digital atlases link their vertical measure to solid marks called datums so that engineers and artists speak the same language when they imagine a new pier or artwork along a seawall. As the moon rises, the map breathes. That slow inhale and exhale is the new legend in the corner, as essential as the compass rose. The coast has always been a musical instrument. Tides play it with a patience that turns physics into sound. In narrow inlets, the standing wave that returns with each flood sets up a note you can feel in your feet if you stand on a wooden jetty. Sea caves act like bottles. As the water rises, it forces air through cracks and vents, and the cliff sings a deep chord that changes with the state of the tide. In certain bays, the geometry supports a slow sway of the entire surface that scientists call a seiche. Fish seem to use these throb rhythms as part of their own navigation. Every coast also has a scrim of small percussive sounds. Bubbles from breaking ripples pop like tiny drums. Pebbles roll back and forth and clatter. The faint hiss that remains when waves calm to barely moving water is the whisper of millions of microbursts where films of air fail. Some cities celebrate this with crafted instruments. There is a sea organ on a European shore where stone steps hold pipes that let waves breathe notes into a promenade. On a still night, the sound is almost like a choral rehearsal. The moon conducts the tempo in silence. People have long told stories to put a face to the moving edge. Fisher calendars etched on wood list lucky hours that match faithful observations of incoming and outgoing streams and the position of the moon in the sky. Stone fish traps built on flats by early coastal communities in many parts of the world show a simple and elegant way to work with water. Curved walls let fish enter during the flood and hold them when the ebb leaves only pools. In northern islands, there are causeways that can be walked at low water to reach a monastery or a fort, and legends that warn late travelers to watch the first trickle around their feet because it means the path will soon be lost. In other lands, the tide is called the breath of a sea dragon who snores when it sleeps and wakes twice daily to visit the shore. These tales are not quaint. They encode an intimacy with the ebb and flow that modern charts only formalize. In the stories, devotion and caution are taught by the same voice. Beyond culture, the tide is also medicine for the sea itself. The deep ocean is wild and strong, yet even this vast body needs its slow stirring. Where a moving tide meets a ridge or a continental slope, it sets off internal waves that travel along layers of density as mountain ranges would guide wind. These waves break far from shore and mix water masses that would otherwise remain stacked like pages. The result is a transport of oxygen into depths where animals live at a slow pace, and a rise of nutrients into sunlit layers where tiny floating plants grow. This invisible conveyor feeds the base of the food web. It also participates in the very large circulation that traps and releases heat and carbon. Part of the energy that drives these processes comes from lunar gravity. In this sense, the moon assists Earth in keeping the ocean from stratifying into a still and separate set of layers. The mixing does not erase structure, it softens it and carries just enough of the deep to the surface, and just enough of the surface to the deep so that life can link its different rooms. When you stand at the shore at night and listen, all of these chapters blend to a single quiet lesson. Engines that turn with the tide need humility and care so that the marshes and fish that share the water find their way through. Distant moons teach us that gravity writes warmth under ice and turns silence into movement 500 million kilometers from our homes. The slow breaking of Earth and the retreat of the moon are the softest ticking of a clock older than mountains. Cities that choose to live by the moon's schedule gain a touch of grace that rigid walls never hold. Mapmakers draw in layers of time as well as space, and the new atlases thrum with tides as living annotations. Coasts are instruments, and even a breath of wind over the mouth of a sea cave can sound like a choir charging itself for the next change of water. People have always read the pull of the moon in their own language, whether with notches on a stick, stones set on a flat, or a song about the breath of a great animal asleep under the sky. And the sea, that patient physician, mixes and cleanses itself by this same gentle force. Now imagine the hour before dawn. The moon is not yet set. The reef hums softly. The marsh waits for the first glimmer. In the channel, a green light drifts as a pilot boat idles near the edge of the fairway, its captain resting a hand on the throttle while watching the clock that blends the tide table and the radio weather. Somewhere far offshore, internal waves roll across an unseen slope and scatter the glow of plankton like the wake of a slow fish. In a river up the coast, a boar gathers for its run, silent as a cat at the edge of a porch. In the far sky above all of this, a small spacecraft passes over the dark earth and pings the sea with radar pulses, reciting the uneven poem of heights and phases that will be read later by anyone who wants to learn the next day's story. The tide turns, the flood begins, currents lean into the piers, sand grains tumble and settle into new ripples that only a gull might notice. The estuary breathes in, and birds lift from their roosts to follow uncovering edges. Houses, set back on their stilts, watch the first thin ribbon of water spread across the lowest lawns of a floodable park by design. On a different coast, the outbreath exposes a chain of tide pools where children tomorrow will learn the names of anemones, because this hour of retreat cleans the basins and sets their calendar of air and sun. Tidal plants upriver taste the easing of salt and pull a little extra sweetness into their leaves. In all these rooms, living things listen. When the tide has filled its shape and slack arrives, a moment of perfect balance settles across the water. There is no hiss on stones, no shear against a piling, only the faintest tremor of sand moving in slow motion. Then the ebb begins, and the cycle repeats, a gift given by a companion world that does nothing more than circle the earth and keep its face turned toward us. The lesson is plain and kind. Power does not require noise. Timing is everything, and patience keeps the bridge between the seen and the unseen strong. The moon asks nothing in return for this lesson except that we pay attention. Let that attention carry you into sleep. Picture the curve of the bay as a gentle bowl and the surface of the sea as a soft sheet that lifts and falls twice in every lunar day. Imagine harbors waiting for their quiet windows, marsh grasses combing the flow, and coral flats reading the calendar written in light and water. Think of ice that flexes with a sigh the size of a continent, and of distant moons that glow inside from the same rhythm. With each breath you take, quietly count the steps of the tide. In your mind, walk the sand that will be wet by morning, and watch the stars reflected in the first trickle across the flat stones. The sea is turning its page. The moon is steady in the sky. The night belongs to their conversation, and you are invited to listen. Let us end this journey with a quiet thought experiment. Imagine a clear night when the sea is calm and the wind is soft and the moon does not rise. the familiar silver path on the water never appears. The shorebirds do not wait for a high tide that is higher than most. The reefs do not glow in time with a full moon. The clocks of countless creatures tick, but they are listening for a bell that never rings. Could this ever happen, and what would Earth become without its companion? First, it helps to say what the moon is doing at every moment, because the answer lives there. Our satellite pulls on the oceans, but also on the rock of the continents and on the thin shell of the air. The result is more than a tide. It is a transfer of energy and a transfer of time. Tidal friction very slowly turns some of the spin of Earth into heat in the sea. That tiny loss of spin lengthens our day by a small slice of a second every century. The same tidal interaction pushes the moon a little farther away each year by a few fingers' width on a school ruler. The moon is therefore not falling toward us. It is drifting outward, and it is doing so far too slowly to leave Earth behind before the distant future when the sun ages and changes into a red giant. In plain words, there is no natural path in the near future by which the moon simply disappears. Still, thought experiments are useful. Let us imagine that the moon were removed by magic, or that we wake to a world in which it never formed. What changes would be immediate, and what would arrive on slow feet? The first change would be written on the face of the ocean. Tides would not vanish. The sun pulls as well, and the sun would still raise the sea. The lunar part of the tide is stronger because the moon is close. It contributes the larger share of the present range, roughly 2/3 in most places. What would remain is the solar part, which is weaker but not small. Every coast would still feel the rise and fall, but the average range would shrink to perhaps 1/3 or a little more of what people know now. Places that thrive on resonance, such as narrow bays that match the natural tempo of a tidal basin, would keep some of their drama but with lower crests. The great stage of the Bay of Fundy would not fall silent, yet its applause would be softer. Smaller tides would change the shape of work along the shore. Harbours that rely on windows of water to cross a bar would have a new timetable. Inlets continually dredged by a swift ebb and flow would collect more sand. Salt marshes and mangrove forests that drink and breathe with the tide would still pulse, but they would spend more hours either flooded or dry, reshaping the mix of plants that can live there. Flats that presently appear at very low water would be revealed less often, and many birds that feed there would have fewer meals. The chapters of life that open when the sea pulls back would be shorter. The second change would be seen in the sky and felt in the rhythms of living things. No moon means no eclipses in the way we know them. There would be no soft rings of light around a lunar disk during a total solar eclipse, and no earth-cast shadow slowly covering the moon on warm summer nights. Moonlight, which is sunlight scattered by rock and dust, would no longer set a monthly lantern over the sea. Nights would be darker by a wide margin, and most people would see more faint stars with the naked eye than at any time in human memory. But darker nights are not only a gift to stargazers. Many animals use lunar light as a cue. Coral reefs in the tropics release reproductive cells in astonishing mass events that line up with the phase of the moon and the timing of spring tides. Horseshoe crabs climb beaches on the highest waters of the month and shorebirds plan migrations to match that feast. Some fish spawn in pulses that follow the lunar cycle, and many predators time their hunting to moonlit nights. Without the moon, these patterns would not stop, but they would detach from a neat monthly signal. Evolution would search for other clocks, perhaps the length of the night itself, perhaps the beat of the seasons, and some species would adapt faster than others. A few might disappear from certain coasts, not because life is fragile in principle, but because life is precise in practice. A deeper, slower change lies inside the planet. The tug of the moon acts on the whole spinning Earth. It is the main hand on the lever that slows the rotation little by little. If that hand were removed, Earth would largely stop giving away its spin to the sea. Days would still lengthen across geological time, but far more slowly. The story of ancient corals hints at this. Fossil corals record growth rings like trees. In some very old specimens, those rings imply that there were once about 370 days in a year. That is a shorter day. The reason is the old dance with a closer moon and stronger tides. Without a lunar partner, the day would not run backwards toward those short values, but the present length would change at a crawl. The moon also steadies the tilt of Earth. Our axis leans by a little less than 1/4 of a right angle, and the direction of that lean wobbles slowly like a spinning top. The moon adds a strong correction to that wobble. Planets without a large moon, such as Mars, seem to suffer episodes when the tilt of the axis can wander from small to very large angles over long spans of time under the combined pull of the Sun and of the giant planets. A world whose axis leans much more than now would have extreme seasons. In one era, the poles might tip toward the Sun for long summers and then away for long winters. Ice caps could grow and vanish, and deserts could migrate to latitudes that are now mild. Without the moon, our own axis would not start swinging wildly overnight. The change would be slow, but the calculations suggest that across millions of years, the tilt could vary far more than people have known, and climate would feel that wandering hand. In simple terms, the moon is a quiet flywheel for our seasons. Another slow change would hide in the interior of the sea. Tides do more than lift the surface. As the tide moves over rough bottom and around slopes, it excites internal waves in the layers of the ocean. Those hidden waves carry energy downward and contribute a great share of the mixing that brings cold, deep water up and sends surface water down. This mixing helps close the global loop of ocean circulation. Remove the lunar part of the tide, and the total mixing energy falls by a large fraction. The deep sea would likely become more stably layered in some regions. Oxygen brought downward would move more slowly. Nutrients stirred upward from depth would be fewer. The great engine that moves heat across the planet would still run, since winds and the contrast between polar and equatorial waters also drive it. Yet its cadence would change. A little less stirring over a very long time can steer climate in ways that are not obvious from the beach. Would volcanoes, earthquakes, or the magnetic field notice the loss? No catastrophe is expected. The moon does create earth tides in rock measured in centimeters, and there are intriguing hints that stress from those tiny flexes can slightly shift the timing of small earthquakes along faults that are already close to slipping. That is a nudge rather than a cause. The magnetic field lives in flows of liquid iron in the core and does not rely on the Moon for power. Plate tectonics is forced by mantle convection and the cooling of the planet and would go on. The Moon is a metronome for the surface and the air and the shallow sea, not an engine for the deep interior. How could the Moon disappear at all? The realistic answer is that it almost certainly cannot within the span of human history. The Moon is drifting outward by a few centimeters each year, but it is held by Earth's gravity, and the two bodies share angular momentum. Over extremely long time, the pair tends toward a state where Earth rotates at the same rate that the Moon orbits, and then both face the same side in a slow embrace. The Sun will begin its giant phase before that state arrives. A dramatic loss of the Moon would require an event on the scale of a giant impact, like the one that likely formed it. That is not part of the quiet future that astronomy expects. Capture by the Sun would require a complex three-body ballet that current orbits do not permit. Fragmentation by tides would require the Moon to move much closer, crossing a limit named after Roche, and the Moon is moving the other way. If the thought experiment demands a cause, then only magic or an impossible accident will do. Suppose the magic is granted. What would people notice the first evening the disappearance of lunar light would make the Milky Way and faint nebulae leap out over the countryside? Sea turtles that use a bright horizon to orient after hatching might struggle for a time, then find new cues such as the shine of starlight on waves. Night flowering plants that open under full moon brightness would shift their timing toward dusk or dawn. Owls that use moonlight to hunt small mammals would have fewer bright nights and might change their patterns. Humans would revise calendars. Many cultures still mark time by the synodic month, the long breath from one full moon to the next. The idea of a month would remain as custom, but its natural anchor would be gone. Mariners would adjust. In a moonless world, the largest storm surges would still occur. Storm surge is wind and pressure moving water. The timing of especially high water caused by a king tide when the lunar and solar pulls align would vanish because there would be no lunar partner to align with the sun. But storm surges would continue to arrive on their own schedule. In one way, that is better, and in one way, it is worse. It is better because a truly dangerous coincidence of a strong storm with an extreme astronomical tide would be rarer. It is worse because people have long used the monthly tidal rhythm as a kind of heartbeat for coastal risk. Losing that heartbeat removes a layer of predictability that sailors and port pilots quietly rely on. Back on land, the long cycle of the precession of the equinoxes would change. That slow drift of the direction of Earth's axis currently completes a full circle in about many tens of centuries. The torque from the Moon is a main driver. Remove it, and the period would lengthen, and the pace of that tiny celestial clock would be different. Calendars that slide stars against seasons over very long spans would need new corrections. Astronomy would rewrite a few tables, and culture would rewrite a few myths. There are questions people ask that are not really physical, but are part of the answer. Would the night be lonelier without a companion disk rising and setting? Would poetry lose a star muse? The truth is that people fill the sky with meaning no matter what lights it. But there is a practical grace in a nearby world that shows phases, hosts eclipses, and ties our biology to a gentle monthly rhythm. Without it, our civilization would not be crippled, but it would feel as if a page had been torn from a very old book. One last question remains. If the moon is not going to vanish, will it stay the same? The answer is no, and that fact is also a comfort. The moon is moving outward. The extra distance will subtly reduce tidal range in the far future as the lunar pull grows weaker. Days will continue to lengthen by tiny amounts. The beat of the sea will slow very slightly. Human beings will not live long enough to notice, but the ocean will. If we step back far enough in imagination, we can watch the whole film in reverse. Early in Earth history, when the moon was much closer, tides were giants that swept coasts with large range and quick rhythm. As the partner moved outward, they softened. The present age sits in the middle of that slow music. There is no cliff edge ahead, only the long fade of a drum that never fully stops. So could the moon disappear? In any practical sense, no. What would happen if it did? The sea would still rise and fall under the sun, but by less. Coasts and marshes would redraw themselves. The inner clocks of sea life would search for new signals. Nights would deepen. The climate would keep its seasons, but gain a greater tendency to drift over very long time, because the tilt of Earth would be less tightly guided. Our days would lengthen more slowly than they do now. Eclipses would belong to memory, and the lesson would be as quiet as a low tide at dawn. A small body far away holds many threads. Pull on that knot, and whole tapestries slacken, for tonight the moon still walks the sky. It leans over the water, and the water leans back. If you listen, you can hear the shore breathe with that ancient exchange. Thank you for wandering through the math and the myths and the living tides. May the soft pull of that distant companion help your thoughts settle, the way the sea settles when the wind drops and the current turns. Rest well, and let the steady rhythm that shaped the coasts of the world carry you into sleep.